Okay, good afternoon, everyone. There's only one last remaining topic, and that is counters. So in digital circuits, you said you have no idea what counters do? Oh, in the lab. Okay. So parallel in, serial out. Oh, actually, I had an example of the parallel in, serial out shift register. I think I just didn't go over that one, but operation is the same as serial in and parallel out, right? Data comes in serially, which is taken out parallel. You can also take the data out serially. I believe I mentioned that. So based on the mode of transmission, input and output, you can have 4 different kinds of shift registers. So this was just an example of parallel in, serial out. Counters, as the name suggests, are used for counting. Okay, it seems like a very simple operation, but it's actually very important in the implementation of logic circuits. Okay, it's very important in the implementation of logic circuits. So the diagram here shows you a 3-bit counter, and it's comprised of JK flip-flops. JK flip-flop is a modified or a advanced version of the SR flip-flop, meaning the unpredictable state where both inputs are high gives us a toggle mode of the JK flip-flop. And that is what you see here. So each one of these is connected to logic high or logic 1. That means that the output of each flip-flop is going to toggle from its state. If it was 0, output's going to be 1. If it was 1 previously, output will toggle to 0. This flip-flop is also known as a toggle flip-flop, a T flip-flop. So T flip-flop has a separate symbol. The input is T and output is Q. For every input of the clock, the output simply toggles. So 3-bit counter, Q0, Q1, and Q2. And the timing diagram looks like this. If we analyze the circuit, we can see that J and K flip-flops are connected to 1. The clock is a negative edge trigger. Again, this symbol is for an edge trigger, and the bubble shows it's a negative edge trigger. So every negative going transition is when the flip-flop will activate, and because it is configured to be a toggle, the output will keep toggling. The output will keep toggling. Now, here the input is simply a signal that's coming in. It doesn't have to be, the signal could be anything. Okay, the signal could be anything. It means we could have a sensor that is connected, like a real life application, we could have a sensor that is connected in there. For instance, if it was a manufacturing, like let's say a food product line, you have items going on a conveyor belt, and it's counting the number of, let's say, packages or bottles, for instance. The counter is counting every time a package passes by or a bottle passes by. A sensor senses the signal here, and so it starts counting. So it starts count 1. Absence of a product, the signal is absent. It doesn't count. It stops. Does that make sense? It's kind of real life application. So in a small self-contained manufacturing system is where you would find, one of the most common applications for a counter. So negative edge trigger, if this is the input going into the clock, okay, it goes into the clock signal or clock input. The output Q0, Q1, and Q2 will toggle between 0 and 1 for every negative going pulse. So the first negative going pulse is right here. 1 second, third, fourth. So every negative pulse is going to trigger the flip-flops into toggling. At the beginning, we say the counter is reset to 0, meaning all outputs are 0. Okay. So it's not shown in here, but there would be a preset and a set and a reset button, right? You clear out the complete outputs and all outputs are now 0. So at the beginning, all outputs are set to 0, right? When the first negative going pulse arrives, Q0 toggles and goes to 1. Output of Q0 is connected to the clock of the next one. Output Q1 is connected to the clock of Q2, and so on and so forth. So even though flip-flops 1 and 2 are activated in the first cycle, even though flip-flops are activated, the input is still 0. If the input is 0, it's not going to do anything. It's just going to stay 0. All right, it's going to stay 0 because this doesn't go negative until here. That makes sense. This input, the clock input, doesn't go negative until these triggers and these edges. The same way, this doesn't go negative until here. So each successive ones do not activate unless and until the edge goes negative. So this input is the clock input for the first one, which is 0, flip-flop 0. Output of flip-flop 0 is the clock input for flip-flop 1. Output of flip-flop 1 is the clock input for flip-flop 2. Right? So each one of those will only get activated when the clock goes negative. Okay, when the clock goes negative. So again, take a look. Output Q0 is connected to the clock of Q1. Output Q2 is connected to the clock of Q2. Yes.
Why is that so different from shift register?
You're talking about here?
Yeah.
Here the clock input is the same. Shift register is just the data, the delay that is coming in. Here the clocks are cascaded. So the output, so the clock input just goes to the first flip-flop, and the output goes to the clock. So it's different from the shift register. So if we take a look here, see, J and K are permanently tied to 1, right? So we don't have to worry about those at all. Those are not inputs right now. Okay, J and K tied to 1. Typically a JK flip-flop, you would say J is input, K is input. But here, J and K are permanently connected to logic 1. So the mode of operation is toggling. The output is toggling. And the first input signal is actually going into the clock of the first one. And then the output of the first one goes into the clock of the second one. And that's the big difference. That's the big difference. So these are building blocks, right? You can take these building blocks and design circuits however you want. And this is another way of, using the features. So again, each flip-flop will only activate at the negative going pulse. Whenever it receives a negative going pulse, it'll activate. And the mode of activation is it flips from 0 to 1. So because it's cascading, when you first give an input, negative going pulse, the first one changes and toggles its value at every negative going pulse. Yes?
So if you wanted to make like a byte,
8 of them, yes. Absolutely. A byte would need 8. Yeah. And nowadays, everything is 64-bit. So 64-bit bus. Anyway, does this make sense? It cascades. It's, yes.
what is in the modeling?
So it's counting. So it's 0, 0, 0 at the first step. So if you take the outputs and combine them, Q2, Q1, and Q0, if you form the truth table where every input, the first is 0, 0, 0. Then Q0 toggles, so it becomes 0, 0, 1. Then it toggles again, so it becomes 0, 1, 0. And 0, 1, 1. So you see, keeps toggling, right? And 1 0 0, and then so on and so forth. And that's what that is showing. And after it finishes 2 raised to 3, which is 8, 1 1 1, which is the 8th count, resets back to 0. Resets back to 0. The change, the clock is rippling through from first stage to the second to the third. And hence the name ripple counter. The clock ripples through each successive state. You can also have the reset function at any one of these intermediate values. And that would be known as a modulo counter. A modulo counter. A modulo counter, a modulo n counter means the counter will reset after it performs n counts. So a modulo 3 counter will perform 3 counts, meaning 0, 1, and 2. And then the next state would be 0, 0, 0. So it will reset to 0. A modulo 7 counter will count 7, meaning 0 through 6. And then instead of going to 1, 1, 1, it would go to 0, 0, 0. So modular math, simplest of terms. How many of you recall that or are familiar with it? Modular math, modulo. Modular is basically if you perform a division, whatever is the remainder is the modulo. So if you divide, the most common example is the clock. A clock is a modulo 12. So if you say 1500 times 1500, 15 divided by 12, a clock resets after every 12 counts. After every 12 counts, it goes back to 1, right? 1, 2, I mean, it goes to 0, so then it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, AM, PM, 2 cycles. But it's modulo 12, right? So if you say 1500 hours, 1500 divided by 15 divided by 12 gives you a remainder of 3 PM. So whatever's the remainder is the modulus. In counters, effectively, it resets the state to 0. So a modulo, yes.
I was like, maybe you were like, but I was like, when the module 6, then it means that
6 counts. You tell me. 6 counts. Where should it reset? No, 6 counts. The first count is always 0. It's a digital binary, so it's always 0. So 0 is 1. Binary 0 is, well, we always say 1. So there are 2 states, 0 and 1, right? But total is 2 counts. You include the 0 in the count, right?
Yeah.
So 6 counts, modulo 6, meaning 6 counts, goes to 0 to 5. So after 5, which is 1, 0, 1, it should go to 0, 0, 0.
Oh.
That's the homework problem. That's the homework problem. That's modulo 6.
Oh, so you also calculate the 0.
Yeah. So modulo 6, modulo counter.
Yeah, binary always says 0.
Yeah. And again, there are so many circuits we can discuss, logic circuits, logic states. There's so many things we can discuss, but we're going to call it at an end right here. Depending on which book we are using, other professors use Rizzoni, which is, if you didn't take if you took another professor's 201 class, they would have used Rizzoni. Rizzoni has some less things from this book and a few other, there are some differences between. So they discuss a few other circuits. They would not discuss these circuits. So this depends on which book you're using and how much the professor wants to go in depth. But I think giving a general overview of binary number system, digital logic, the gates, which are the fundamental building blocks, the basic flip-flops, and then we have seen a lot more flip-flops than we actually need to. But going up to JK flip-flop and toggle mode, shift registers and counters, I think that is more than sufficient. So I will call a halt to chapter 4 after counters. Yes.
So we don't have any examples with parallel.
If you want, I can even provide a quiz if you want.
No?
No, not in the exam.
Okay,
No.
I was like,
Now, exams will, mostly just quizzes and homework, not much, outside of that.
I never-
Typically, I don't. Even in my 201 classes, I 201, 321, strictly I stick with the text. I mean, again, I can, there are in my evaluation, sometimes students will write, the professor just talked about what was in the textbook. Well, the purpose is because I'm going to teach from the textbook. I could take things, if I want to make it difficult, I could pull problems from like multiple different sources, not even textbook, like, research papers. I would read research papers, so I can come up with like problems and circuits from there. But then, what's the point? I want to make sure the students learn without worrying about the grades too much. So if there's too much pressure, then students don't learn. So that is kind of my approach. Yes.
For our products, we expect to see rapid fire.
What is rapid fires? Oh, rectifiers. We did rectifiers, right? Yeah. I haven't decided. I haven't set the exam yet. I'll probably do it sometime tomorrow. So yeah. Again, homework problems. So what I'm going to do is I'm going to sit and review all the homework problems and everything we did in the quizzes and pretty much everything we did in the homework. So if students study the homework problems and the quizzes, you should be in good state. Speaking of quizzes, I'll be posting the solutions sometime today. Yes. Yeah, I need to do it. I started 5 days ago, and yeah. I mean, everyone does. I mean, all the students do too. So yeah, I do have 5 preps, which is, yeah, it just, this quarter just worked out like that, unfortunately. Typically, I would have like 2 or 3, which is enough, but I have more than 150 students across all my sections. Yeah, I'm looking at it, but it's not showing up. Oh, there it is. All right, let's see.
So that is not in the title anymore, no?
No. Good news is this is for like general knowledge, not general knowledge, but technical knowledge to give you a brief overview, but I'm not going to test this on the exam. So I should have said that after I finished talking so that you all pay attention. But you may as well know, I'm not going to test students on chapter 5. Okay. Chapter 5 is just something I'm adding because we have some time to talk about it. So early on in the days of analog computers, those computers were used to perform mathematical operations, okay? And they occupied huge rooms. So there'd be like peripherals where you had a memory storage in another room, or like you'd have a big warehouse, you'd have a separate section. You'd have memory storage in a separate section, you'd have the processing unit in a separate section. And so there was one central location where you had the main processing unit. It would be basically the size of this big room, analog computation. And hence the name central processing unit, CPU. So in modern computers, when they built out of solid state devices, they carried over the same nomenclature, okay? So we have a central processing unit, which is your CPU, the processor that we use. It comprises of a control unit and mathematical operators, which was known as the arithmetic logic unit, ALU, okay? So typical computer architecture till today consists of a CPU, and then you'd have access to some sort of storage or memory, and then your input output devices. Depending on what kind of system you have. Typical ones you're familiar with: display outputs, serial ports, parallel ports, USBs, right? Thunderbolt ports, FireWire, if anyone remembers those are all would be your input output buses. So computer architecture basically would comprise of the simplest of things. Now, this is like a huge block diagram. If you go inside, each one of these is a very, very complex circuit, right? But this is the basics of computer architecture. Central processing unit will have access to a clock that synchronizes all circuits. Again, without a clock, everything would be I mean, everything would be haywire. Nothing would work correctly, right? So there's a clock signal on there that synchronizes everything. You have your CPU. The CPU communicates with everything in the CPU bus. The CPU bus is basically the number of lines addressing the memory. Initially, the first processor in the world was the 4004 from Intel. It was a 4-bit processor. Then came an 8-bit processor, a 16-bit, then 32-bit CPUs. And then a few years ago, we moved to 64 bits. So the CPU bus is 64 lines of addressable memory. The reason we all moved to 64-bit is because access to memory locations, binary form again, 2 raised to n. If it's a 32-bit system and n is equal to 32, you can only access a maximum of 4 GB of RAM memory. So 32-bit operating system is limited to only accessing 4 GB of memory, 4 gigabytes of memory. That was the big limitation. So 64-bit processing came along a few years later, and now all computers, whether it's mobile devices or desktop devices, they all run on 64-bit processors. There are even higher bit for like supercomputers and other specialized operations like servers and stuff, which are higher number of bits, where they require addressing large amount of memory. Anyway, and then let's see. It accesses volatile memory. Volatile is so called because the storage in those bits, in those registers, disappears once the power is cut off. Hence, volatile memory. It does not stay constant. Basically, that would be the RAM, random access memory. RAM stands for random access memory. Comes in 2 flavors, static and dynamic. And then you have non-volatile memory, which is flash and EEPROM. Yeah. ROM stands for read-only memory. They classified it. When I first learned, it was like random access memory and read-only memory, meaning 2 different things. One is talking about how it is accessed. The other one is talking about how the memory stores permanently. So the first ones that came out were read-only memory, meaning it's the chip is designed from the factory, and you can only read from it. You cannot program it. Then came the programmable ROMs, meaning you could take the chip, you could program it in-house and use it for your application, but you could not reuse it once you actually program it. Then came erasable EEPROMs. Erasable PROMs had a small window where you could shine UV light through that window and erase that chip and reprogram it again. And then came EEPROM, which is electrically erasable, programmable read-only memory. And those are the kinds that are still used in in some tools to this day. Okay, and we need EEPROMs again because, well, again, depending on the application, if they've been around for a long time, it's dependable, it works, and so where it doesn't need to be reprogrammed every so often, they have a long reliability, and so they use EEPROM in many tools and equipment in this modern age. And of course, the other kinds of memory are the NAND and NOR-based flash memory, which we know as solid-state drives, SSDs, which is inside most laptops and most desktops nowadays. Okay, those are all flash-based memory. Okay, and they can be, they have non-volatile memory, meaning you can take the power out, and they would still hold the data. They will still hold the charge inside the devices, meaning whatever state the transistor is left in, zeros or ones, will stay in the memory even if the power is off. Yes.
That's the reason why they're called flash, or?
No. I don't know where the name came from, but yeah. I mean, there is a history behind everything, but yeah. Let's see. Digital IOs. A to D is analog to digital converters. D to A is digital to analog converters. Most of the sensors would be analog sensors. And so you would always need an analog to digital converter. So analog, like a microphone, would be an analog to digital converter. Well, sorry, not analog to microphone is a transducer, takes audio signals, converts it into electrical signals, and those electrical signals are analog signals, and there is a A to D chip inside either the microphone or inside the computer that would take the analog signals and convert it into a digital form. So you need an analog to digital converter. Then you perform all of that processing. That processing is performed by an audio processor known as, there are DSPs, digital signal processing, again, a separate course by itself in electrical engineering. There is image processing, IP. And nowadays, of course, it's a big deal because all mobile devices have cameras in them. And so all of that processing is done by DSPs and IPs. Anyway, so at the other end, you need a digital to analog because once it goes through a process, whether it's filtering out unwanted components, whether it's amplification, providing gain, equalizer, you still need to convert that digital signal back into analog to output to a speaker. So you need a digital to analog converter at the output end. And so all of those interact with the CPU via the CPU bus. Okay, via the CPU bus. Then, how do we interface with computer systems? Well, we can interface. A machine basically doesn't know what it's doing. We have to tell the machine what to do. So if we talk to the machine directly, we program the codes directly in there, we're talking to the machine directly, and that is said to be a very low-level programming language. Anytime we talk to the machine, we have to use a program or a programming language, okay? The lowest level is known as machine language or machine programming. It is also known as assembly language. So the lowest language level is known as machine language or assembly language. And I did this back in 1993, I think. And assembly language programming is uses a hex keyboard, and you have to program direct codes into the machine to tell it, and you tell it what to do. And it's still used to this day. So anytime you want to talk to a machine directly, engineers would use assembly language programming, which, as you were saying, you are learning in mechatronics. So there is a use for that. Especially as non-E images, you might be interfacing with with a piece of equipment in your own field, and it might use assembly language. At the higher end, you have all the higher level programming languages, which is what you sit at a computer and you type it up in the keyboard. There's a compiler inside that actually changes your high level language into low level language and sends it to the machine. So high level languages, the most common ones, if you want to learn programming, you should start with C programming. And you have C++, and nowadays, of course, there's Python. So all of these are examples of high level language. And so there's a compiler in there that will compile it and translate it into a machine language by a compiler. CPU registers, of course, are used for memory storage. They would store the information. Interrupts, well, there's a lot of other things we're talking about, but interrupts is basically CPU has many tasks, right? It's interfacing with the audio system, the display, graphics processing unit, PCI bus. There's lots of other things. And so every time a CPU needs, every time a component peripheral needs to talk to the CPU, it sends an interrupt signal. And so that is basically what is known as an interrupt. Okay, and you can set a priority, low, medium, or high, depending on what the application is. Now, as development happened over time, things started shrinking. But you do not always need a very powerful processor to do the simplest of tasks, right? Like if you're just running a simple machine, you don't need to stuff a Core i7 processor in there, right? So for that purpose, we have what is known as a microcontroller. It is used for a specific purpose. Many companies design microcontrollers. There are specific programming languages that you can use to talk to these microcontrollers. Basically, a microcontroller, excuse me, a microcontroller would be it's not the most accurate description, but I would say a very low-level processor. Is that? Sometimes microcontrollers, depending on the configuration, would include some memory in there. So RAM as well as storage. But most of the time it's separate. Okay. So again, the purpose is the same. You want a microcontroller that is not that powerful, but is good enough to handle the application, specific application, right? So you have the digital sensors and the analog sensors that are feeding input into the microcontroller, and the microcontroller sends the output. And from the output, well, it can do whatever functions you want. So many of the smart appliances that we see nowadays, well, not smart appliances, but the appliances that came before the so-called smart appliances, they have microcontrollers in them. So if you take your dishwasher or a dryer or a washer, they will all have some sort of microcontroller chip inside it. Yes, do you have a question?
Like optical encoders and things like that.
No, encoder is just an encoder. Yeah. It just encodes information. This is an example of one of the most popular microcontrollers. You may perhaps have used it. You may have heard of it. It's the ATmega 328P microcontroller, more commonly known as the Arduino microcontroller. So this is also an example of a reduced instruction set computer, or RISC, RISC. And I'll come back to RISC. But it has two 8-bit bidirectional IO ports. There's an analog voltage reference, reset pins, connections of ground, digital output pins plus 5 volts and plus 3.3 volts, all in this chip. And there was a group of researchers in Italy sitting at a bar. The bar or a pub's name was named after King Arduin, Arduin. Ancient Roman king or Italian king, I have no idea, Arduin. And I don't know how drunk they were, but they were brainstorming. As they say, all the good ideas come from a pub. They were brainstorming about something that would make prototyping very easy for kids, researchers, people everywhere. You don't have to be an engineer to use it. And so they came up with the Arduino project. They took that microcontroller and created this board that is known as the Arduino Uno board. And uses, the chip is right here and comprised based on the chip and a lot of other components on there. You can create anything you want, well, anything as in within the capabilities of the board. You can create and prototype lots of different hardware as well as software. Programming this microcontroller board is very easy, or relatively easy. Even if you have no knowledge of the program, you can still buy these kits and well, use it for like learning. How many of you have used this before? I'm sure some of you have. Just one, kind of. Oh, okay, Raspberry Pi. I have that one too. So there's a large library of high-level functions available, meaning some other person has compiled the library, and all we need to do is we need to just use that library, the instruction in the library. Everything is based on the instruction set, meaning the machine needs to know what it needs to do. So that's known as an instruction set, right? So you can either talk to the machine directly and tell it that, oh, I want you to do this at this time, then go here and take this, and then take this data and do this, this. Or someone else has already compiled the code and creates a library, and all you have to do is basically use that one or few word instruction, and the machine does the rest. Yes. So the program is usually written in C, C++.
It was like set, and it has already the word settings. So like,
What do you mean settings?
I mean, it was like, I mean, you can simply pick the button, put it like if and then. I was like very confused.
Yeah, that's C programming though.
Yeah.
It's, yeah, you can. I mean, it's part of the C program if you want to use that. Yes. So I used this during the pandemic. I was teaching E251 online, and I created an online version. So every student would sit in their own residence, They would purchase their own kit. The kits, they are unbelievable. If you buy this separately, it's about 10, 12 bucks. If you buy the kit, it's about 30 bucks. Probably now the price might have gone up a little bit, but the cheapest ones are still around 30. And you get a ton of like sensors and components in there. So again, this board by itself is at least 10. The kit comprises of like 100 pieces of resistors, temperature sensors, magnetometers, soil sensors, water sensors, humidity sensor, all kinds of sensors in there. And so you can see here, I used a digital temperature and humidity sensor and an analog thermistor to measure the temperature. And you write the code and you program it. So depending on what you want to do, you simply write the code and you program it or flash it in the chip, and it'll tell you what it needs to do. We measured the voltage using reference voltage of 5 volts. So again, depending on the calibration, output's a little bit off, but we are measuring 4.79 volts. Here it was measuring 51% humidity, 26 degrees C. So this is digital measurement, and this was analog. And it's a low power mode, meaning you can take a battery and you can hook this up and you can place it anywhere you want. There are ultrasonic sensors in there, and you can create robot cars along with this. So people have done like really, really cool things with this. You can buy prepackaged kits. It's a really cool way of learning about, especially if you're into mechatronics at all, then it's a really, well, I mean, for $30, it's a very good deal. It comes with a breadboard and components. The sum of all put together is much cheaper than individual components. If you go to buy everything individually, it's probably cost you close to 100. So it's incredible how they actually managed to sell it for only 30. Anyway, that's the Arduino project. Then we have the Raspberry Pi, which is actually a full-blown computer by itself. The purpose, again, by the founders, and there's a Raspberry Pi Foundation, is again the same thing, is to get every person in this world interested in working with, well, computers and computing. And so, as you said, he was working with our Raspberry Pi a bit. This is a full-blown computer. It's amazing that it's basically smaller than the palm of my hand, and it's a full-blown computer. It has a CPU, processor, memory, HDMI out, RAM storage, Wi-Fi, Bluetooth, 4 USB ports, Ethernet, everything. You can run entire operating systems on the Raspberry Pi. Okay. Yep, there is. Yeah, you can run Windows. And then we come to the modern day age of system on a chip, SoCs. And SoCs are now everywhere. All the mobile devices use system on a chip. So the problem with older, well, not problem, but as the technology went along, when they first came up with, let's say, not smartphone, like the mobile phones, if you remember, really big Motorola phone that was like a cordless phone. Anyone remember that? Somebody does. And the reason for that was all the chips were separate. Your processor was separate, your memory is separate, all of them were individual chips. More importantly, your modem, the baseband chip, that is separate. Everything is separate. And slowly but surely, they started integrating everything into one package. And the system on chip simply with the simplest explanation is that you took all of the different chips and put it on one piece of silicon. Okay, and that is what system on a chip stands for, SoCs. So modern day SoCs started incorporating everything in one. Qualcomm is one of the biggest chip designers, and their SoCs, they have a big advantage because they did a lot of research, bought companies, and they have several patents relating to communication. So even before smartphones came out, even before they started designing these kind of chips, their whole money was here in the modems. Modem is an acronym for modulation and demodulation. When you send information, you have to modulate that signal. And when you receive it, you have to unravel or demodulate it. So modem stands for modulation and demodulation. Okay. Modulation and demodulation. That's what AM and FM stands for. AM stands for amplitude modulation. FM stands for frequency modulation. AM modulation. Well, I have time. A modulation is basically if I want to take a piece of paper and I want to send it across the room, is it going to go far? No, right? But well, the other side is now gone. Wow. Other wheel. I'm gonna leave it. I'll find the request. Anyway, so if I want to send the signal on the other side of the room, it's not gonna go far. If I take a piece of stone, or let's say a heavier piece of some metal, and I wrap the paper around and now I throw it, it could go out the window as far as I can throw it, right? Amplitude modulation is the same thing. If I stand here and talk, I might be able to talk somebody like 15 or 20 feet, not gonna go farther than that. But if I take the sound signal the sound that I'm making, and I modulate it with another frequency signal, then that can travel farther. So amplitude modulation basically takes audio signals, mixes it up with a higher frequency signal, and sends it out the window. And at the other end, you have to demodulate everything. And so that's what a modem does: modulation, demodulation. Anyway, Qualcomm makes most of the money in the communication chips. So lots of companies make SoCs. Broadcom is another famous one. Broadcom made several chips for wireless routers. It's also the main chip in the Raspberry Pi. All of these chips share one thing. They're based on the ARM architecture. What was the joke?
He said that all these things have one thing in common. He said electricity.
Yeah, that is funny. It is, yes, they do. But I was talking more in terms of like design. So ARM, if you haven't heard, stands for, well, it doesn't stand for anything now. It used to stand for Advanced RISC Machines. So the company is a UK-based company. And no, RISC is RISC. So ARM stands for Advanced RISC Machines, and that came about after Apple pushed them to actually change it. Previously, they were known as Acorn, like not an acorn, so Acorn RISC Machines. Okay, Acorn RISC Machines. Then they changed it to ARM. I mean, they kept ARM, but they changed it to Advanced RISC Machines. And now they say it doesn't stand for anything. It's just ARM. It's like ESPN. Now it doesn't stand for anything. Anyone know what it stands for? Entertainment and Sports Programming Network. ESPN used to stand for Entertainment and Sports Programming Network. Now as in like, I don't know how many years ago, but they decided it's not an acronym anymore, it's just ESPN. So ESPN. So ARM used to stand for Advanced RISC Machine, now it's just ARM. Anyway, it has become hugely popular because of the explosion of mobile devices. They used to make chips for the small, microcontrollers, small projects, stuff like that. All they do is they create reference designs. Okay, this is a real world implication. They create reference designs, and other companies buy those designs. If they have the license, they can change it. They can do whatever they want with it. So Samsung, Apple, Qualcomm, all of these companies, they don't design their own. I mean, they design their own things, but it's all based on ARM Holdings reference designs. Apple, they infused money into ARM Holdings. So they started designing their own chips years and years and years ago before they switched to Intel. They used to design their chips and you had them made by IBM, if y'all remember. Power processor, PowerPC, the ones that came right before like 2007. Then they switched to Intel, but Intel chips are ASICs, application specific integrated chips, integrated circuits. Those are much more power intensive than they need. So Apple started designing their own chips again, starting from the smartphones. And they used ARM Holdings reference designs to do that. Then after that period, they stopped referencing those designs. They only licensed ARM instruction sets, and they now do their own designs. They do their own designs, and if you remember a few years ago, I don't know how much you follow the news, but they started integrating more and more chips onto their own Apple silicon. or they say Apple silicon as in like the chip that is designed by Apple. So you had the motion coprocessor, then you had the image processor, the camera processor, everything. They started everything one at a time every year. Every single year they kept making improvements. So their SoC, the chips that were like spread out are now onto one SoC chip. And that's true for like Qualcomm and Samsung and everybody. None of these companies makes their own chips, by the way. All they do is design. They don't know how to make them. If they want to make them, they have to go to Global Foundries or to TSMC or Samsung Semiconductor. That was the big deal because Samsung makes their own chips. They make display panels. They make memory storage. Samsung is the world leader in making memory storage. So fabrication wise, the processor that is in Apple's circuit or in Samsung's or in any other device is made by like a third party foundry, which is an expensive business to get in. Intel is the only one in the world that is like the biggest player in the world. I wouldn't say the only, but the biggest one that can actually design its own chip and manufacture its own chip. There are many other foundry makers, but slowly but surely they started, flowing by the side. But that's the modern day and age, right?
I was telling before that you have something like Snapdragons. I remember when.
So Snapdragon is just a brand name that Qualcomm came up with.
Yeah, because.
Here, where is it? Where did you see it?
Oh yeah, that's
Yeah.
Snapdragon.
Snapdragon is basically the name that Qualcomm gave to one of its, to its SoCs. So system on a chip for Qualcomm, that is Snapdragon.
Yeah.
So most likely, if you have a non-Apple phone, like an Android phone or like a Microsoft phone, if anyone does have that, they would be using the Snapdragon chipsets.
Yeah.
So that's what Snapdragon is. The worldwide chip shortage happened because, well, there were several reasons. There were hurricanes or typhoons in other parts of the world. In Taiwan, so the factory shut down. I think there was a water shortage. And then last winter, if you remember, there was a big power freeze, a big power cut and freezing weather in Texas. That's where Samsung Semiconductor has their factories. And so that put together with going on climate change in other parts of the world, well, let me not involve politics in it, but because of inclement weather, there were issues in manufacturing chips. Now what happens is all the chip manufacturers are going to invest. If you have reduced capacity, what do? You only produce whatever makes you the biggest profit, right? Well, that's what they started doing. Something that's only does the biggest profit. Automobile manufacturers, they don't need the latest and greatest. In a vehicle, you only need a small microprocessor or microcontroller, but you just need it to work right. All kinds of conditions, whether it's hot weather, salt, sea air, very cold weather, doesn't really matter. Vehicle manufacturers just need their chips to work right. So they were all older process technology. And so when all these problems came about, all the manufacturers and foundries shut down the older processor nodes. And that's why there's a global chip shortage, especially in vehicles. Now, a lot of factories are coming online. So in the next, not this year, but 2023, 2024, there's going to be a glut of chips in the market. So hopefully prices will come down after that. Yes. Now it's it's the Raspberry Pi 4 or something. So it's been a while. Couple of final things. Chapter 5, again, there's not, I'm not going to ask you, I'm not going to test you. This is, again, just general purpose of going forward. I will update the final exam page. If you're planning to take it on Saturday, just, make sure you let me know in the survey. And then I will have on there, it's about, 5, anywhere between 4 and 6 problems, not more than that, okay? Solely based on the homework assignments and the quizzes. Won't go anything outside of that. Also, my goal every quarter is to ensure that every student should feel that they have learned more during the course of the quarter as they're walking out of the room than when they first walked in. Hopefully, all of you feel that way too. And one final thing was about course evaluations.
What's the percentage?
So far, let's see.
Okay, 10.
So 10 of 36, I haven't refreshed the page yet since this morning, so. I don't know if anyone has. So it's still 10 of 36.
Okay.
So, so there's extra credit evaluation, extra credit built into the entire homework. And it's also something that I hand out for the course evaluations. I bring this up just to let you know it's completely anonymous, whether you believe it or not. The only thing we see is the number of responses. We don't even get these back until like the beginning of next quarter, right? So staff in the university compiles like hundreds of courses together, and then they compile them and they send them out like sometime after spring break. So on Friday, when it closes on Friday midnight, whatever number is here, every student will get extra credit applied directly to their final grade in the amount of the response rate. So if 18 of 36 students have responded, then it's 50% response rate. So every student will get 0.5 extra credit points applied directly to their final grade. If 36 of 36 students respond, it's 100% response rate. Every student receives 1 extra credit point towards their overall grade.
Last quarter, we got 0.89.
0.89. So,
Yeah.
well, again, it's anonymous. It's fair to everyone. Whether you participate or not, you benefit.
Guys, 201's kicking our butt. We can't let that happen.
Yeah.
Come on.
So quiz on Friday. Last quiz on Friday. Anyone?
Last quiz on Friday.
I was just kidding. No class on Friday. Take the time. No, take the time to catch up on your work, study, or catch up on sleep if you want. All right. I will see you all during final exam time. Have a good quarter.
Dr. Tran, did you get my email that I sent to you the other day?
Which email?
I sent you an email that